So this is Physics 1420, second semester of algebra-based physics. Sorry the screen is gone from in here. You can't really see the screen. I mean, can't really see what's on my screen that well, but hopefully you'll get the gist of it. We won't cover too much today. Let's see. We have syllabus here. You can read along with me here. So this is our, doesn't really show up all that well on there with this weird background here, does it? That's all right. We'll zoom in on it here. You can read that up there, right? Okay, so syllabus is like always, just get all the information for the class. We're reading here 11 to 11:50 this semester. And the beginning and ending of class, of course, my office. I will be around Monday, Wednesday, and Friday mornings until early afternoon for any time you want to come in and visit me. I highly recommend you just call me or email beforehand if you want to visit with me so that I know to be here. Tuesdays and Thursdays I will be out and about doing things. I may be here, I may be on North Campus. I've got a big project I'm working on for UNL, a big project working on for the museum here in town, so I'll be busy. But I will make time if you make an appointment to come and see me if you'd like. Of course, you can also contact me through my open math at any time. This class is all about electricity, magnetism, and optics, pretty much when it comes down to it. Those are the three things we're going to cover. If we have time at the end, we will also maybe go into modern physics. We could even do some thermal physics and waves, although I think we covered both of those in first semester for you guys, so I think we're okay. But anyway, well, most likely we would go into modern physics if we had extra time. Modern physics being things like atomic physics and quantum mechanics and things like that. That's a fun one to go into, especially if you're interested in the medical fields. So we will try to cover that because I think both of you are interested in medical fields in some way. Is that correct, Daniel? I can't remember what you're doing. Oh, right. You're doing aviation. Well, even for aviation, those things are interesting. But particularly for aviation, electricity, magnetism, optics are very, very useful because they're used a lot in avionics. So anyway, regardless of your interest, this is a really interesting semester. I think far more interesting for most people than the first semester. We'll be using the same textbook, same My Open Math, except it's a different course ID and enrollment key to get into the course. So those are what they are right there. If you want to jump into them now, if you don't want to jump into them now, I can email this to you. I might as well just email it to you all right now, I suppose, so that you all have it. Let's see. Folkers is your last name, right, Daniel? Is it okay to send it to your Gmail?
Yeah, that's fine.
Okay. Why don't I have yours? I'm sure I have it somewhere here. There we go. And then our last one. Okay. So I will attach this here really quick so that you guys can jump onto My Open Math. Apparently Let's see, I can't remember how to do this. Oh, here we go. That's where it is. It says it's in downloads. That's not, I didn't see it in downloads anywhere. That's stupid. There it is. That's not all. That's also not it. Where did it go? I don't know. What's that? Oh. Did we ever look into an internship for you with Trigo Dugan?
Yeah.
Did you find an opportunity there or not? You did.
It didn't work out too well, but yeah, I'm just taking that one class this semester with them.
So you're taking ground school?
Yeah.
Okay. Well, that's actually a really good experience there. That's a great class. Are you going to take any flight lessons?
I haven't looked into it yet.
Yeah. They're expensive, but they're fun. Okay, let's see what's going on here. There it is. Found it. Okay, there's your syllabus. I'll send that to you. That took forever. So once you get into MyOpenMath, of course, you know how that works. You've all used it before. Everything else is all pretty much the same. Any questions at all? Okay. Let's see. Now what's going on? There we go. I actually created a quiz for today. How about that? So I'm going to change this so that it's not hidden anymore. So you can actually see it. So let's see. Do either of you have your computers with you? You have your computer, you have yours with you? Let's see here. So I have a quiz. Without Michael being here, I'm not sure if it's fair to quiz here. Well, this is not the quiz I want you to do actually, because I already know all of you. I was thinking it was an electrical quiz. Let me see if I did the next one. I didn't do the next one. So never mind. Let's not worry about that quiz for now. Let's get rid of that. All right. All right. So anyway, the labs are here. Of course, this. Obviously, I didn't really do a good job of updating this, but it's somewhat updated. Due dates. That's the next thing that we need to look at. It looks like we do have due dates. We have homework due on Friday right now. Does Friday work out for you guys, or do you prefer to have a weekend day to work on them, or what?
I prefer to have a weekday, just in case I have stuff pop up.
Okay, do you prefer to do it Saturday or Sunday?
I mean, I always just like plan things for Sunday, but if it's on Saturday, I don't mind either.
Okay, do you have any preference?
Yeah, it doesn't matter to me.
I think we'll do it Saturdays, because on Sundays, if people email me with questions, I'm just not answering emails on Sundays, so that's my day off from everything. So we'll make it Saturdays. We'll fix that really quick here. Let's see, what's the fastest way to do that? Probably here.
Odds are I'll have it done before then, but just in case.
Yeah, it is always a good idea to have your homework at least all worked on before it's due, so you can ask your questions. But we'll go ahead and move these. Now, the exam, right now we have 2 exams scheduled, just 22 through 27 and the final. Do you have a preference on when the exam is scheduled? Right now it's scheduled for a Wednesday. Does that work on Wednesday, or would it be better on a Thursday, or what?
So I have a reading listening on the 27th. That's the only thing that I can't. I'm not going to be able to be around a whole lot on the 27th.
The 27th of
January.
January? We don't have anything planned for that day. You're good. So this day, which it looks like to be the 6th, there's 2 exams. Chapters 18 through 21 and then 22 through 27. Both on Wednesday, not a problem for anybody to do those Wednesday. Okay. Homeworks we'll have due Saturday. The final exam. Look, right now we have one more chapter than we have weeks, so we'll probably be able to fit both of these in. Actually, this final week. Because we don't really do a lot of homework in the final chapters. It's mostly just learning about things, watching videos, doing activities. And there's actually a few chapters here in the middle where we won't really even meet at all. We'll pretty much take an entire week off to do optics, where you're just gonna do experiments on your own all week long. And you'll have a homework assignment, but the homework assignment is just very closely tied to the experiments, and the experiments are short and pretty straightforward, but they're kind of interesting and fun. It's fun to play with the equipment. It's fun. Optics is a fun, probably my favorite of all the experiments, just because it's so tactile. You know, you're seeing these things happen. It's kind of cool stuff. But anyway. We'll get back to that. Okay, so that's the schedule. It's all put together now. Homework due on Saturdays, a couple of tests on Wednesdays. They're all here. And we start off with Chapter 18, Electric Charge and Electric Field. So, electric charge and electric field in Chapter 18 starts off with this great picture of this kid sliding on the slide with his hair standing up, right? This could have been all of my kids. All of my kids, I have pictures like this of them. Not so much when I was a kid. When I was a kid, the slides were all made of metal. You didn't get as much static electricity in your hair with those slides. It was still possible, just not as much as plastic. And why is that? It's because materials transfer charge back and forth in different ways depending on the materials themselves. And this is something that was discovered many, thousands of years ago. They knew about this. Thousands of years ago, people knew that if you were sleeping in your cave at night in a bear skin or something like this, and you were tossing and turning in your sleep, the bear skin would stick to your hair or your skin, and so you'd get up and you'd have bear hair on your skin stuck to you. And it was obnoxious because it wasn't just stuck because, sweat or something. It was this weird sticky thing that you couldn't tell what was making it stick. It wasn't something obvious. And it was 2,000 years ago when the first scientist really started to kind of figure these things out. About 2,000 years ago, let's see if they have, it was a Greek guy, I can't remember his name. But anyway, this Greek philosopher slash scientist was observing how amber, when it's rubbed with fur, gets this property where the fur will stick to the amber after a while, or the amber sticks to the fur, or vice versa, right? But there were other things that were noticed later on as people continued doing experiments with this. So this, 2,000 years ago, and the interesting thing about this one also is that the Greek word for amber is electra, and that's where the idea of electricity came about. When Benjamin Franklin named the electron, for example, I think it was him that named the electron. They started to think that maybe these were particles carrying this charge back and forth, and they said, well, let's name one of the particles after electron, call it the electron, right? For sure, he gave the electron a negative value for its charge. But anyway, they said, well, there are other materials that do this, and other scientists started to study this. Hundreds of years later, about the time of Newton, over 1,000 years later, about the time of Newton, other scientists were doing experiments with other materials. And one of the things that they discovered is that if you do an experiment with two materials by rubbing them together and they start sticking to each other, if you do it with amber and fur, for example, and you do two pieces of amber with two pieces of fur, and then you bring the fur close to each other, the fur actually repels. If you bring each piece of fur close to each other from the two different pieces of amber. And if you bring the two pieces of amber together, they will actually repel instead of attract. Right? So that's different. That's not as simple as just two things attracting each other, because two things attracting each other was something that we're familiar with. That's like the earth and the sun attract each other. And at that time, at the time of Newton, they understood attractive forces. That happens. But repulsive forces, this was new. Repulsive forces were not common. There was repulsive forces of magnets, but no connection scientifically at this point between magnets and electricity, because magnets back then were just rocks that you dug up. Those were the only magnets they had. So they didn't really understand any kind of connection between electricity and magnetism at the time. By the way, amber is just fossilized tree sap, if you're not familiar with that. May have seen it in like the dinosaur movies, Jurassic Park movies, right, where this tree sap covers the mosquito that bit the dinosaur, and then they make a new dinosaur with it. Kind of funny, but anyway. So they started to when they first started looking at this, they're like, well, this is a weird thing that's going on. What could be happening? And then as they realized that there's both attractive and repulsive forces involved, it complicated issues. There's another problem with it as well. The other problem is that there are some situations, and here they show charging up two things so that they attract, and then two things so that they repel. But another problem with this is that there are other situations, and let me see if I can find a picture of one here. Here's a situation that's a little complicated. And if you rub a balloon on your sweater, for example, and then bring the balloon over to the wall, it will actually stick to the wall. And yet you didn't rub anything on the wall. And that complicates things even more. Right? And so as they were doing these experiments and trying to figure them out, they learned a lot of things. One of the first things they learned is that, of course, there's attractive forces and repulsive forces involved. Another of the first things that they learned is let me see. I'm trying to get them in the right order here, and I'm not going to get them in the right order, and then I'm going to screw things up. Let me open my other book here, because I think they have a list of them in the right order. Yeah, here they actually have the names of the people too. So, so William Gilbert is the guy that studied doing this with different things. He did crystals and glass and other gems and wool instead of fur. He even did metals. So let's see here. Where's the list? Here we go. So one of the other things is, and they actually don't have an order in order either, but let's see. So one of the other things that this guy discovered, Gilbert, is that some materials do this really well. They charge up really well, or they create this effect really well, and others don't do it as well. So, for example, amber or other things that are polymers like plastics and rubber and amber, these are all polymers. They're all these organic molecule kind of things. They really charge up well with fur. They just do a really good job with natural hair. So that's why balloons charge up really well on our hair and stuff like that. Whereas things like silk and glass, they will charge up, but they don't do it nearly so well. You know, glass is not a polymer. Silk is not really like fur at all. They'll do it, but not very much. And that metals hardly do this at all. It's not even measurable, really. And then another thing that they discovered is that you could actually transfer this effect from one object to another. So you could take one balloon and rub it in your hair really good and charge it up really good, and then you could take it to another balloon and touch it to another balloon where you touched it to your hair, and then that new balloon would actually repel the other balloon that you rubbed it with. They would both get a little bit of charged, but only if you touched it in the same place that you touched your hair. But then they also discovered that you could take the charge off of the balloon that you charged with your hair, and you could put it onto metal. So you could touch it to some metal, and then the metal would repel the balloon. So you could transfer it to the metal, but with the balloons, it always stayed on the same side that you touched. But with metal, as soon as you touched it with the part of the balloon that was touched, the entire piece of metal would be charged. So you could move the balloon to any side, it would be repelled from any side of a metal sphere or a metal box. So in other words, this effect on balloons and other things that were not metallic stayed in one spot wherever you rubbed it against something else. But if you transferred that effect to metal by touching the charged object to metal, either the fur or the balloon, it spread out all over the metal. In other words, it moved somehow. And this started giving rise to the idea that these charges were carried by particles. Because if it could move, it was obviously a thing, a particle, right? And so they started thinking, well, maybe there's two kinds of particles, because that fits what we're seeing here. If there are two kinds of particles, then you can rub your amber with your fur, right? And each of these objects will have both kinds of particles, but they're balanced out before you start rubbing them together. There's equal numbers of each particle. But when you start rubbing them together, for some reason, some of the particles move to one of the or other, or maybe both kinds of particles move or something. But in any case, no matter what, you're going to get an imbalance later, so that one of these things has more of one particle and the other one has more of the other particle. And we're going to say that opposites attract and like particles repel. And that's the only thing that fits these experiments. If you said that like particles attract, that wouldn't fit the theories that we've come up with so far. And they're theories because we can't see what's going on. They're completely theories. And so they came up with these things, we call these thought experiments, where you can't really see what's going on, but you kind of make a theory and then you apply it to the experiment and say, could it be this way? And you follow it through logically and draw some pictures and say, yeah, it could have happened this way, because in this particular case, when we rub the amber against the fur, we're going to say that some of the negative particles from the fur jumped over to the amber, and the amber now has this excess of negative particles, and this over here now has an excess of positive particles because it lost its balance of negative particles. And so now they attract each other. And if you had two pieces of fur that you'd done this with, then they would propel because both of them would have a lack of negative particles and an excess of positive particles. Excuse me. At the beginning, they didn't really know which ones were moving. And this is actually why Benjamin Franklin assigned the negative to the electron, because he thought the electron was the one sitting still and the positive one would be doing the moving. And with the math, you actually want the positive to be the one that's moving. If they were both moving, that would negate that, no pun intended, that necessity. But they suspected that one of them was kind of sitting still and the other one was moving. And the reason they suspected this is because they figured that these particles came from the matter of the material. They were part of the mass of the material. And when they were moving charges around, there was no real movement of mass. It didn't change the mass of the cloth or the amber really at all, in no measurable way. And so they figured that one of these particles had most of the mass of the object and the other particle was very tiny and had very little mass. And they were getting a lot of information from their experiments. From all their logic, they were starting to understand that, yes, it's true. We've taken this to the point. Excuse me, I got a tickle in my throat now. We've done so many experiments to this point following this theory that we're like 99.999, pretty much 100% sure that there is a particle that carries a charge, a positive charge, and is pretty much sits still and carries most of the mass, the vast majority of the mass in these things. And we call that the proton, right? In reality, there's also another particle that even carries more mass than the proton, which we call the neutron, but they didn't know about that at the time. The neutron is very difficult to detect because it doesn't have any charge to it, right? Charge is easy to detect because of these experiments. So, but they eventually discovered that it was the positive charge that was sitting still because of these experiments, and the negative one that was moving. And then they're all, dang you, Thomas, not Thomas, but what's his name? Franklin, Benjamin Franklin, for choosing the wrong one, because now all of our electricity equations have a negative sign in them that they didn't need to have. And we never changed it back because it was too late by then. But another thing that was discovered later on is that you could build up this charge. Now, this is something that Benjamin Franklin did. He built this thing that's called a Leyden jar, where he put foil on the inside of a jar and foil on the outside, or metal of some kind on the outside of a glass jar. Didn't have to be glass; it could be clay also, or anything that wasn't metallic, pretty much. And then you put this metallic rod down the middle of the cork, and you connect it to the inside foil just by hanging a wire in there or something. And then you could touch balloons that were charged up to the top of this rod, and the charge would jump onto the metal, and they would build up. And you could build up a lot of charge. I mean, it could almost be dangerous, these jars. If they got big enough, physically big enough, they could hold more and more and more charge. And the reason they could hold charge is because as the charge built up on the inside, and in this particular case, they're showing a positive charge on the inside. So really what you're doing is you're going to bring a balloon to this, and it's going to attract electrons from the metal, and the metal is going to give electrons to the balloon, and then it's going to end up positively charged metal on the inside. And the outside will essentially start to attract electrons from the air, from people touching the jar or whatever. It'll start to attract electrons from the outside. And you could actually connect the outside of the jar to the ground to suck electrons up from the earth. And it would just build up electrons on the outside, where you get a lack of electrons on the inside, and it balances out the whole jar, so the whole jar can just keep building up more and more until you physically can't fit any more electrons on the inside. And this is also something we call a capacitor. We use these kind of devices in electronics today all the time. The original one was called the Leyden jar. So, and this you could use these. You could build up enough charge on these to get, like a little shock of lightning across a short distance, and all kinds of stuff. Led to all kinds of understandings. Other experiments that were done with force. This guy named Charles Augustin de Coulomb, a dead Frenchman of the physics world, he did a bunch of experiments in the 1700s measuring the amount of force between charged objects. And other people did lots of experiments measuring force between charged objects. Another guy did an experiment where he elevated particles using electrical charge. He elevated charged particles using an electric charge below them so that they would be suspended in gravity. So gravity's pulling them down, these electrical charges are pushing them up, and he was actually able to measure the amount of charge on all these little dots of oil that he was using. He was using little droplets of oil. And in his experiments, what he discovered was that every charge of every little dot of oil, and they were tiny droplets. Like he used a one of these things that they call them atomizers, but we talked about them in the last semester when we talked about pressure, where you lower the pressure above a fluid and it releases these tiny little droplets of fluid. But anyway, the atomizer is what they used for perfume back in the old days. They make such tiny droplets that you can almost count the number of atoms in each droplet. That's how small the droplet is. And these tiny little droplets would have a tiny amount of charge, and he was able to measure the amount of charge by balancing it in the gravitational field. And he was able to measure to an extremely high precision. And what he discovered is that each one of these droplets had an integer amount of charge. Like this one had twice as much as this one had 8 times as much as this one had 7 times as much as this one, but it was never 3.5 times as much as this one, or 1.7 times as much as this one, or anything else like that. The ratios were always integer ratios. And that means that the charge of these particles has a minimum amount. It has a specific amount that it is always. In other words, electrons always have the same amount of charge. And that's it. And it turns out that protons have the same amount of charge, except it's positive. And that was discovered doing these really ingenious experiments using really old equipment back, hundreds of years ago. So all these experiments were done, and what did we learn? Well, we learned these things here. Charge is quantized. It has a certain amount that it is. 1.6 times 10 to the minus 19 coulombs, named after the guy that discovered how to measure charge. He was measuring it in what we now call coulombs. And the electron has that much, the proton has that much, and nothing else no particle can have less than that if it's on its own. Turns out there are particles that have less than that, but those particles can't exist alone. And all other particles that have charge are made up of integer amounts of this. 10 times this, 1,000 times this, 252,563,451 times this, or whatever. It's always some integer amount of this because it's always some integer amount of electrons or some integer amount of protons. It is quantized. The quantity is fixed by integer amounts, right? The magnitude of the charge doesn't matter if it's positive or negative. That doesn't affect the quantization of it or anything like that. Charge is conserved because it's connected to actual particles, and particles can't be destroyed or created. It's there, and it's always there. It's always been there. It never goes away. You can cancel out charge. You can have this much negative charge and the exact same amount of positive charge, and for that system, the total will be 0, but all that charge will still be there. It doesn't disappear. It doesn't get created. It's conserved. Charge was created at the beginning of the universe and has never been destroyed or created since without conservation. And in closed systems, you can take advantage of this by essentially bookkeeping your charge. I have this much charge in my system right now. 10 minutes from now, I have to have that same amount of charge, no matter what it's done or where it's gone. That's how much I have to account for, and so you can take advantage of that. All right. Another experiment that was done by Rutherford, before they actually figured out that what the electron and proton were. They didn't actually think that the proton was a particle. They thought the electron was was fairly easy to detect as a particle. Um, they knew that one particle moved, and so there was a particle involved, in other words. What they didn't know was what this positive charge was all about, and at first they just thought, well, maybe it's just stuff, you know. And there was most of this was being done in England at the time, so they likened it to a bread pudding, or a what's the word for that? What do they call it? At Christmas time, they eat it. They eat some kind of pudding. But anyway, they eat this. They call it a pudding, but really it's just a cake. Yeah, that's what we call a cake. And this cake usually has bits of fruit in it, right? So they likened all matter to like cake, where, you know, you're made up of this stuff that's kind of like homogeneous throughout, and it's just like a cake. And then every once in a while, there's this negatively charged electron poking around in there. And when you're doing your experiments with your balloon, that's what leaves you and goes on the balloon. And the rest of that stuff that's just kind of like spread evenly throughout your body is just positively charged stuff. Just pudding stuff, cake stuff. And that stuff carries all the mass, because the electrons don't move much mass back and forth. So all the mass is just kind of spread out into this cake stuff, right? And that's what people thought of when they thought of atoms, first started thinking of atoms. The idea of the atom was thought up 2,000 years ago by a guy named Democritus, who also came up with democracy, actually. One good idea, one that didn't work out so well. You want to guess which one is which? Turns out democracy seems like a great idea, but when you give people, when you give the people their decision to how they want to do things, they generally choose what they want and not what's best for them. That's why democracies never work. We don't have a democracy, by the way. The idea of the atom came up way back then. And he said, you know, when you break things, when you break a rock and you keep breaking it, and eventually you'll get to a piece that's so small and so fundamental that it cannot be broken. That was his theory, his philosophy. And he called it the atom because in Greek, the word atom means indivisible. So it's the unbreakable piece, the smallest piece possible, right? As that theory developed over hundreds and thousands of years, eventually they started thinking, well, maybe the atom is an actual particle that involves these charges, right? And maybe it's just like a cake. It's a little cake. And we're made up of a bunch of these little cakes. And each cake has its raisins in it, and that's great. Well, along comes Ernst Rutherford, and he said, well, I'll put that theory to a test. If it really is a cake, then I should be able to shoot smaller, more concentrated cakes that are really fast, and I should be able to shoot them right through those bigger, less concentrated cakes. Because there were these small concentrated cakes that they called alpha particles, and they came out of things like uranium. So he took uranium and he stuck it next to another cake called gold. And gold was a nice object for this experiment because gold can be hammered out into a really thin layer. We call it gold leaf, right? And it can be hammered out so thin you can almost see through it. So it's literally only maybe a few dozen atoms thick. So it's a really thin piece of cake, right? But what that does is it allows particles like these alpha particles to go through. Alpha particles are positively charged. They have 2 positive charge in an amount of 3.2 times 10 to the minus 19 coulombs in them. And when they come out of uranium, they're cooking. They're moving super fast. They can embed themselves into your skin, and they will go right through gold foil, essentially. Especially if it's hammered super thin. It's like they don't see the atoms at all. It's like they just burrow right through the cake and come out the other side. Well, the theory was that as they went through this cake, they would pretty much just go straight through all the time, except every once in a while they would come close to one of these electrons and veer off path a little bit. But not a lot, because the electrons don't have enough mass to pull them off path along, right? The alpha particles have a lot of mass, these little ones don't. So it's like shooting bullets, through a cake. They're just going to go straight through pretty much. And that's what he saw. And he saw some of them veering off a little bit. But on the 1,000th bullet that went through, something crazy happened. The bullet came straight back at him, and he's like, oh crap, this theory is out the window. Something in this cake is so massive and positively charged because it repelled my positive bullet but it's so massive that it didn't move at all because nothing big came out the other side. But this big bullet did come back. So he had to revise the theory. So instead of saying there's this stuff that's like cake, they say, well, there's a massive thing in the center, and that's where all the mass is. And in between the center and all the electrons is just nothing. And that's why stuff just goes straight through. It's not because of any cake, but all the mass is concentrated at this one spot. And that one spot is 1,000th the size of the atom. And that's it. The atom is all concentrated in this 1,000th of the atom size ball of stuff. And it has all the positive charge and all the mass. And when we get our 1,000th shot through this thing, it finally hits that little piece and comes straight back at us, right? And that's where they came up with this new model of the atom, which we call the Rutherford model. And the Rutherford model is basically the model we use today. There are some very important distinctions between what we believe and what they believed then, but it's basically the same idea. That the electrons are kind of floating around out there on the outside. Originally they thought it was kind of like planets going around the sun or something, but the idea is that the mass is concentrated at the center and all the positive charge is concentrated at the center, which brings up some really crazy things, because how do you get all that positive charge so close together? Because it all repels itself, right? And so and this was happening in the 1800s, and in the 1900s they started to figure that out as well. It came down to the discovery of the neutron. But anyway, so all these things are just offshoots of these experiments that have been going on for thousands of years concerning charge, static electricity, essentially. Right. So this guy, James Chadwick, discovered the neutron. Hard to discover because, of course, can't detect it. Not repelled by anything, not attracted by anything. But they knew something was there because they started to realize that the mass of these things was much bigger than accounted for the amount of charge that was involved. And eventually they ended up using wax to discover the neutron. They actually started trying to eject particles out of the nucleus by hammering the nucleus with things and trying to shoot things out of it to see what was in there. And they discovered, hey, there's this thing coming out that's making a little track in the wax. It literally would just like make this little line in the wax that they could see under a microscope. And it certainly was not charged because it wasn't being attracted by electric charges in any way. So they were able to discover the neutron. And you're like, man, that's such an antiquated way to discover something. But it's actually not that far off from the way we look at neutrons today. We just don't use wax. We use different materials. We use much more complex materials. But anyway. So many things discovered, so many things came as a result of this. And this is the beginnings of what we're studying in this class today. Here they take a step that the other book doesn't and talk about conservation of electrons in modern physics. We actually do know that you can destroy an electron, but you can only destroy it by using what is called an anti-electron or a positron. An anti-electron is a positively charged particle that has all the same attributes as the electron, except that it's positively charged. It has everything about it is an electron, except it's positive. It's a piece of antimatter. And antimatter is pretty rare, or it's at least very difficult to detect if it's not rare. In that case, it's probably what we call dark matter. But anyway, antimatter is something that is rare to find, rare to detect out there in the universe. And usually, just about the time we do detect it, we detect it in a situation like this, where an electron meets an anti-electron and annihilates. They actually make each other disappear. And in that case, charge is conserved, because before you started, you had an electron and an anti-electron which add up to zero charge. And when they annihilate, they disappear. They completely annihilate each other. And the only thing that's left is some energy. There's no mass left. There's no charge left, just some energy. And the energy comes out in the form of light usually. And that anti-electron collision annihilation results in zero charge. So charge is conserved because there was zero before when you added them together, and there's zero after because it's gone. So that's charge conservation. There are situations also where there's an amount of energy that can actually create an electron-anti-electron pair. And this happens in big super colliders. They make antimatter pairs in Chicago, where they have a big super collider. They make them in California, where they have several super colliders. I think the closest one is probably the one in Chicago, although there might be one. There's probably one in Colorado. I know there are some in Colorado, actually. So the closest, I don't know if they're doing any in Lincoln. I doubt it. But anyway, probably the closest place they're making antimatter is in Colorado. And oh, that's not true. We make antimatter right here. I forgot. We actually have right here in North Platte. We actually have a PE machine, a PET machine. You ever seen that at the hospital? So it's in their imaging department. They have a PET machine, which stands for positron emission tomography. And they actually have a collider in there. It's essentially, they accelerate particles into a target, and it creates antimatter. It creates positrons. And they use those to image things, to look at things in people's bodies. You've seen that? So I always forget that they have a positron emission tomography machine here. I think they have two of them, actually, maybe three. But they're actually making positrons.
They use those a lot in the dental offices too.
Yeah, and the great thing is they create those positrons. I didn't know they use them in dental offices at all, but I know that. Anyway, as you create the positron enters somebody's body and it annihilates with an electron and creates energy, and they detect that energy and they use that energy to image something that's going on in the body. So it's kind of cool, but they're not making huge amounts of them. They're making small amounts and then immediately recombining them. In Chicago, they're making huge amounts of positrons, and then they're actually accelerating those positrons through a big accelerator and creating other collisions afterwards. But you can actually see this happen. So I mentioned before that we used wax to detect neutrons. They actually use bubbles to detect antimatter in what they call a bubble chamber. A bubble chamber is a super excited liquid that has bubbles in it, and it's not easy to create. This is what they look like. They're huge. This is a bubble chamber. This is I don't know where this one is, but this is like a couple stories tall, and the fluid inside here has to be in a super excited state, so a lot of energy in it, very high pressure, very high energy. But when you look at the tracks in a bubble chamber, they look like this. This is actually this is more what they actually look like. So they have this fluid that's passing over a screen that's lit up so you can see what's going on, and there's a magnetic field passing through them, but each one of these little curly-cued tracks is either a piece of matter and antimatter, and for every one of these there's another one. And sometimes they start and are created, and sometimes they end at the end of one of these things. And they're able to you can see this is where the energy began, and this is where the two particles went in different directions, because one of them's positive and goes one way, and one of them's negative and goes the other way. So these bubble chamber, I've actually seen the bubble chamber in Chicago, the one that they use there in their experiment. So it's kind of cool stuff. So there's so many cool things that happened because of this theory that there were two charges. Now, if we look at this, little experiment here, we can actually watch the charges change hands here. So let's reset our balloon. We have a nice balance of charges here. We have our wall over here, and we have our sweater here. So if we take our balloon and we rub it against the sweater, we gain electrons on the balloon, and then it's attracted to the lack of electrons on the sweater. But what happens when we bring it to the wall? The extra electrons on the balloon are actually repelling electrons in the wall. So what happens when you bring the balloon next to the wall? It's also attracted to the wall because it's repelling electrons and it's leaving some bare protons that don't move in the wall. So it's two different things. Over here we have imbalance of charge on both. Over here we have a movement of charge in one and an imbalance in charge in the other that causes this. So it gets much more complicated than you can imagine. If you bring this balloon next to a stream of water, the water will be attracted to the balloon for very much the same reason that the wall and the balloon are attracted, right? So there's a lot of complexity in this in these systems, just because we have two particles instead of one. That complexity it gets magnified pretty quickly, and that's all we have for today. You can get started on some of the homework with this what we talked about so far. So go ahead and take a look at that. Like I said, we'll try to get you some lab equipment on Wednesday. Have a great day.
That makes so much sense.
Opening your eyes to the world of charge.
So you're doing like that whole experiment as a kid where you like take a balloon and you charge it and put it next to like a faucet.
Yep.
Running.
Well, can you imagine how complex it'd be if there were 3 charges? And guess what? In some of the natural world, there are more than 2 charges, and more than 3 even. Well, no, 3 is the max we've discovered so far. But it's not electrical charge, it's a different kind of charge.
This class always makes me want to be an engineer though. I was going to ask, where did that big telescope go? I was trying to measure for...
Oh, I took it home for a while. It's right here.
Okay. Oh, cool.
I took it home and I was doing some stargazing with my family and friends over the break a little bit here and there.
Yeah, I was looking for it. I was trying to measure for the new one of these guys.
Yeah. Sorry about that.
No, you're good. I was just like, oh my gosh. I definitely brought it back, right? Like, I for sure did. I got this cool thing. It's like an attachment to the lens, the main lens. And you put it on there and it attaches to your phone, and then you can... Like,
Yeah, I've got a bunch of those.
Oh, you do?
Yeah, when I bought all the little ones, I bought a bunch of those. So I have a bunch of those in storage somewhere. I think they're actually in one of these cabinets.
Yours are Bluetooth though, right?
No,